Good evening. My name is Adam Waxman, and tonight I am here to present Phase 1 of my capstone project conducting comparative analysis of classifier performance and generalization using saccade-related potentials. The basic motivation for conducting this project is to advance the domain of human-centered opportunistic sensing. Opportunistic sensing, as described by Kapadia and colleagues, essentially describes using small computational devices carried by individuals which sense information that relates to their activity and state. In my case, I'm focused on better understanding how biosignals that can be used as targets of opportunistic sensing may be used to accurately infer useful information about what an individual is looking at and the significance of the thing that the individual is looking at. As such, I'm interested in datasets which include both electroencephalogram or EEG data and eye motion data, both of which can be recorded during free movement with mobile recording setups. This line of research is beneficial for many applications where automated remote inferences about cognitive states can improve safety or provide insights that are not necessarily available through direct remote communications. For example, there's neuroscience research which suggests that decisions to perform a motor function finalize prior to an individual's conscious awareness that they have made that decision. So this basically, the decision to move occurs before a person is aware that they've made the decision, according to some research. Anyway, this suggests that a sufficiently streamlined sensing interface might be able to assist faster than human reaction times if, say, someone is about to pull their hand away from dangerous machinery. An automatic interface sensing that they've made that decision could automatically shut off the machinery faster than they move. Another application for this line of research is aggregating sensory input from multiple people simultaneously, which is obviously far more efficient than individual to individual communication. And in a related application, sensory information from a team of individuals can be aggregated to assess whether or not their collective awareness could be improved in some way with feedback. Next logical question about this project would be, why use machine learning to process this kind of data? First, while this is not exclusive to machine learning, the goal of automated understanding of human state and activities has many clear advantages, from reducing reliance on manual evaluation by trained human experts in applications, and ultimately to integrating these automated state assessments with other software, such as the emergency machine shut-off example I mentioned. Second, an advantage to machine learning is that it's capable of processing many different modes of input together and finding patterns that relate them to some output, which aren't necessarily easily to uncover by traditional methods by human investigators. And so the application of machine learning modeling methods to infer state from recorded biosignal data is a steadily growing area of research. In the Wang, Nie, and Liu study, a linear SVM classifier was trained on a dataset of subjects watching movie clips to infer whether they were experiencing positive or negative emotional state based on the EEG signal data. The Zemblis study utilized a random forest model to categorize different types of eye tracking movements with a superior level of accuracy compared to traditional statistical methods, or traditional automatic statistical methods. Finally, the Yoshida study trained a linear SVM regression model to predict features that strongly differentiate between high and low cognitive load driving situations by using driver eye tracking data and basic information about the vehicle state, such as the accelerator, pedal, and steering angle. And going back to the automated information, this study was specifically motivated for developing smarter driver notification systems, which may hold off on notifications during high cognitive load situations. Now, the specific dataset I'll be using to train models on comes from a 2017 experiment conducted by Brouwer and colleagues. In this study, the goal was to train a classifier using simultaneous eye tracking and EEG data to differentiate between visual search targets and unrelated visual stimuli, and also to train a classifier to be able to predict when a subject did not properly encode a search target into their memory despite looking at it. The main visual search task was a monitoring task in which 15 evenly spaced locations on screen would highlight one at a time and display letters which indicated whether or not that location was a target or not. After all locations had been highlighted, the subjects would be instructed to pick all the locations that had shown targets using their mouse and then submit their answer. The experimental manipulation of the study was that in some blocks of this task, the subjects would also need to listen to numbers played over audio and subtract all of them together to a total, in addition to the main task. The condition where they had to do that math task is called the high cognitive load condition. During the low cognitive load condition, the audio would still play, but subjects were instructed to ignore it. The classifier chosen by the researchers was a linear SVM classifier, and overall it performed both classifications at around 60% accuracy. That's classifications of hit and miss versus classifications of looking at target versus looking at non-target. Next page shows some figures from the paper that illustrate that task and results. So on the left, it shows a sample of how the experiment appeared to subjects, along with measured dimensions of the visual field and the spacing between locations. And so the lower left visualizes how the experiment looks when a location is being highlighted. That location shows the letters OK, meaning that it's not a target that needs to be remembered. The targets showed the letters FA instead. Figure 7 on the right shows the classification accuracy results split by experimental condition, the target classification feature, and the feature sets used for different rounds of training. The low load condition has no hit or miss results, shown by the red bars, because there were not enough mistakes during that condition for proper analysis. And this slide just details some of the properties of the dataset. It's available through CAN-CTA's site on appropriate request, though access also requires an account with the SFTP data repository server. Anyone who's interested, you can email me and I can get you in touch with who you'll need to contact about getting an account on that server. And Anyway, the experiment repository contains both unprocessed and minimally processed data, and the minimal processing is really just time synchronization of events. And this is according to the EEG study schema spec level 1. Currently, I'm trying to work with the minimally processed dataset since pre-processing methods are not my focus. Task events and eye tracking are stored in TSV files, but the EEG data, like I mentioned, is stored in MATLAB compatible formats. And because of this, it's taken me longer to get started on the exploratory data analysis. And so for my specific proposal, I first intend to replicate the results of the Brouwer study with the linear SVM classifier, and then apply other classifier models to the data to see if they can achieve better accuracy results. After this basic comparative analysis, the classifiers which are able to perform significantly above chance will be trained again only on data from individual cognitive load conditions and then tested against data from the opposite cognitive load condition. And this will see, based on the testing accuracy, whether the models are able to generalize. This is an important question because it can provide further information about how algorithms which use this kind of data should be trained for applications, like whether high and low cognitive load conditions should be involved in future training for application level models. My suspicion is that the high load condition will generalize better than the low condition than the other way around, because I suspect the EEG signals will reflect a wider variety of cognitive states and thus offer more potential for robust classification. And these are the references I've been relying on so far. Thank you for watching.